Okay, we meet again. So in part 2 of this lecture, we're going to learn further about the design process of the butterworth filter. So as mentioned in part 1 of this lecture, these are the things to be obtained, which the first one are the filter order. Number 2, the first one is the filter order. Number 2 is the cutoff frequencies. Number 3 is the transfer function. Okay, so before we can proceed with this process design, we are going to basically understand the basic principle of the butterworth filter. Yeah. So let's have a look at the next slide. Okay. So in this particular lectures on the butterworth filter, I'm going to use a low pass butterworth filter as a reference. Yeah. In which the high pass and band pass butterworth filter can be modified. Yeah, from the knowledge of the low pass design of the butterworth filter. So you can refer to table F5, yeah, table F5 in the attachment of the filter design. So I did give you this attachment in the e-learning. Yeah, so this attachment will be supplied to you. So you don't have to memorize anything from this attachment. It will be provided to you. So just concentrate on the butterworth column or butterworth information. Yeah, so the in this particular attachment, there are two filters being described. The first one is Chebyshev and number 2 is butterworth. So we just go into the butterworth. So these are the important equations for the butterworth filter, and you're going to use this in the next slides of lecture 19. Okay, so you're going to use this later on in the first page. The second page, we have table F1, which is the calculation for the normalized stop band frequency. Okay, which is the calculation of WSN. Okay, we're going to learn this after that. Yeah, we're going to use this table of this. Okay, F2 is for the Chebyshev, so just ignore. Yeah, just ignore this table F2. F3 is also for Chebyshev, also ignore this table F3. Table of F4 is also for Chebyshev, we can ignore this table. And table F5 is the important things for the butterworth. Yeah. So this is what I meant by the transformation. For instance, if we have the low pass filter, the transformation is S over omega C for the butterworth. For the high pass filter, the transformation is omega C over S for the butterworth, and so on for the band pass and the band stop filter. What is meant by this? So we're going to learn further on this table F5 after this. Yeah. And table F6, both F6A and F6B are the tables for the Butterworth polynomial. Also, we're going to learn about this Butterworth polynomial in the slides 19, in the slides of lecture 19. Yeah. Okay, so let's have a look at this particular lecture 19. Okay, so I did mention to you just now that we are going to use low pass Butterworth filter as the reference in this lecture. Okay, so let's proceed with the low pass Butterworth filter. Yeah. Okay, so this is the magnetic response for the n order low pass Butterworth filter. Okay, this is the equations that can be obtained from the first page of this attachment. If I can refer back to this attachment, the first page of this concentrate on the Butterworth column. Okay, this is what we call this transfer function. Okay, 1 over set of 1 plus omega over omega C to the power of 2n. Yeah. Okay, never memorize this. It will be provided to you. Yeah. Right. And okay, where omega C is a 3 dB cutoff, and n here is the order of the filter. Yeah. So this is the equations for the magnetic response of the n order low pass Butterworth filter, and this is obtained by Mr. Stephen Butterworth. Yeah. Okay, this is the equation from Mr. Stephen Butterworth. Okay. We can then we can also have what we call as a normalized transfer function, which mean the omega C is equals to 1 for the n order low pass Butterworth filter, where the equation is H and S equals to 1 over B and S. And 1 B and S is what we call as the n-order Butterworth polynomial. Yeah, and it can be obtained from the last page of this attachment. Okay, last page of this attachment. So this is the Butterworth polynomial. So basically, table F6A and table F6B are the same. Okay, are the same. Both are the same. Just this is in terms of the equations, polynomial, and this is in terms of the factorized form, but both are the same, yeah? So we can see that we have n is the number of order for the Butterworth polynomial, and these are the coefficients of the Butterworth polynomial. For instance, if we have n order equals to n equals to 3, we are supposed to get only A1 equals to 2 and A2 equals to 2, which is equivalent to this, yeah? S plus 1, S squared plus S plus 1. Okay, so for the B and S here, for n equals to 3, is equals to this Butterworth polynomial of n equals to 3. You can substitute A1 and A2 in this equation. Yeah, we're supposed to get S power of 3. Yeah, S power of 3 plus A2 S power of 2 plus A1 of S plus 1, where A2 and A1 are equals to 2. Yeah, both are equals to 2. So we are supposed to get S power of 3 plus 2, S power of 2 plus 2S plus 1. And it should be equals to this equation. If we expand this equation, we are supposed to get the same as this. Yeah. Okay, so this is the examples of calculation of the Butterworth polynomial looking at the value of n equals to 3. Yeah. And the same thing is applied for the rest of n. Yeah. Hopefully it's clear about this issue. Lah. Okay, so we have learned about two topics, the two main things here. The first one is the magnetic response of the Butterworth filter of n order, and then we also learn about the normalized transfer function of low pass Butterworth filter. Yeah. Okay, so the design of the Butterworth filter will be based on the Butterworth polynomial. Okay, this is what I mentioned just now. Okay, it's very important for us to understand how to calculate, how to obtain the normalized transfer function, because it will be used to design the Butterworth filters. Yeah. Okay, I did mention just now, BNS can be obtained from table F6A and F6B, right? And I give you the same example in the slide. If we consider a transfer function for the third order, so the Butterworth filter transfer function, yeah, the normalized transfer function, H3S will be equals to 1 over B3S. Note that this is what we call as a normalized transfer function, yeah. So it'll be equals to 1 over S plus 1, S squared plus S plus 1. Okay. All right. So hopefully by now you have understand about the usage, the importance of the Butterworth polynomial. Yeah. Okay. Right. So this is this slide shows us how to determine the filters order. Okay. So the filters order can be obtained by using the steps here. Okay. So we have this equation, which is a calculation of the magnitude, yeah, of the amplitude response. Yeah, the gain can be calculated as 20 log of Hj omega, and we are going to get the value to be negative 10 log of 1 plus omega over omega c to the power of 2n. So this is obtained from this magnitude response. Okay, so by using a logarithmic terms for both sides, yeah, 20 log of Hj omega will be 20 log of 1 over third of this. So this will lead us to these equations of alpha. Okay, so we're going to have equations number 1 in terms of dB. Okay, and basically the gain here is actually representing the lines, yeah, representing this line, a straight line here. Yeah, this will be the gain in dB. So we can have two different portions. We're going to have a portion of the pass band and a portion for the stop band. So from the first equation here, we're going to have two distinct bands. The first band is when we consider a frequency between 0 to omega p. Yeah, this is for the passband. So we are supposed to get alpha p. Yeah, the gain for the passband region will be negative 10 log of 1 plus omega p over omega c power of 2n. Yeah, we just substitute omega to be omega p and alpha to be alpha p. Okay, so this equation number 2 is the gain for the passband region. Yeah, the gain for the passband region. Whereas if we consider a stopband region, from equations number 1, we just substitute alpha will be alpha s and omega to be omega s. So this equations number 3, which is the equations of the gain at the stopband region, will be denoting the gain line at the stopband regions here. So now we are supposed to get two equations. The second equations here, equation number 2 is the gain equations for the passband. The equation number 3 is the gain equations at the stopband. Okay, right. So just to remind you again that you don't have to memorize these equations here. So everything is given in this slide. Yeah, in this first page of the attachment. Yeah, you don't have to memorize all of this. Okay, so then from equations 2 and 3, we can manipulate them. Yeah, we can manipulate. You can try this on your own. You're going to get equation number 4. Okay, and end up we're going to have the filter order n by these equations here, which is log 10 of this divided by 2 log of this. Okay, again, these equations for the filter order is given in this attachment. Yeah, this page. Okay, so in this attachment, the n, we have these equations here, log 10 of divided by this one divided by 2 log omega Sn. Okay, this omega Sn is described in attachment on this table F1 with calculation of the normalized stopband angular frequency. For a low pass filter, omega Sn will be omega S over omega P. For high pass, it will be omega P over omega S. And these are the equations for the band pass and band stop filters. So our interest will be only on the low pass or high pass filters. Okay, which means that if we consider a low pass filter, because we are using low pass as our reference, the omega Sn will be omega S over omega P. Yeah. So in these equations here, omega Sn will be omega S over omega P as shown in equation number 5, because again, we are considering the use of a low pass filters. Yeah. If let's say we use a reference of high pass filter, equations of this omega Sn will become omega P over omega S as given in the attachment. Okay, so following this, we can say that we can have two equations for the cutoff frequencies. If permit me to refer to the previous page here. Okay, from equations 2 and equations 3, we are supposed to have two value of cutoff frequencies. The first cutoff frequency omega c is obtained from the gain at the passband, okay, alpha p and omega p. The second value of cutoff frequencies can be obtained from the gain at stop band, alpha s and omega s. So that is why we have these two equations here. Number 6, yeah, which is obtained, the first omega c is obtained from the equations from the gain at the passband. The 7 equations here is the cutoff frequencies obtained from the gain and the frequencies at the stop band. So we are supposed to get equation 6 and equation 7. Okay, right? So hopefully by now you have understand the important equations in the Butterworth filters. Okay, and you have understand how to use the attachment. Yeah. So I'm going to stop here. So in part 3 of this lecture, we're going to proceed further with the design techniques of a low pass buzzword filter. Okay, see you after this.